shown in the figure below are two point charges located along the x-axis. Determine all the following at the point x equals 0 and y equals 8. A, determine the electric field. This problem is the easiest of the three problems dealing with electric field for point charges. And the reason this is the easiest problem is because this problem exhibits a symmetry. Notice that the two charges are the same amounts, plus 4 microcoulombs, and that they are the same distance from the origin. Furthermore, the place at which we are to do our calculation, the point P, is located on the origin. As a result, we're going to be able to effectively do this calculation in a single step. However, we must be very careful in the process of formulating that single step that we remember that electric field is a vector quantity and must be treated as such. To emphasize this point, I am once again going to make a fancy table by which we respect the vector nature of electric field by listing both an x and a y component, and I'm going to consider our problem to have two electric fields that I will label as E1 and E2. In this problem, however, we must recognize that we can use our intelligence to save a large amount of time in the calculation. Looking at the figure itself, we can already imagine the direction of the final electric field. Because of the symmetry between the two charges, the electric field at the point P will not prefer left, it will not prefer right. The electric field at the point P must be in the vertical direction. Therefore, going down to our table for E total, we can say that the electric field will have a y component, but it will not have an x component. What this means to us is something very important. We do not have to calculate the x component of E1, and we do not have to calculate the x component of E2. The reason is, if we did do those calculations correctly, we would get two equal and opposite numbers, and when we added them, we would get 0. Therefore, we can save the calculational step. Furthermore, when we compare the y component of E1 to the y component of E2, these two must be equal to one another. Therefore, we don't have to calculate the y component of E2. Having calculated the y component of E1 is more than sufficient. So that our final result in this problem will be that the y component of the total electric field is equal to twice E1y. So, calculating a single component of a single electric field vector is going to be sufficient to give us the answer. Now let's go ahead and do that. At the point P, due to charge 1, which I'll call the one on the left, we will have an electric field that I'm going to label E1. I'm going to make a triangle, as always, to assist in the calculation. The hypotenuse of this triangle is going to be the line that connects the charge to the point where I'm doing the calculation. This has a length r as part of the r squared in the electric field formula, and the triangle is a right triangle that includes the origin at the corner. We've already seen that the x-axis has a value of 6, and the problem itself tells us that the point P is located a distance 8 up the axis. If you think about it for a moment, this is a familiar triangle. A famous right triangle has sides of 3, 4 for the two legs, and 5 for the hypotenuse, because 3 squared plus 4 squared is equal to 5 squared. Here we see that one axis is double 3, another axis is double 4, and so in fact the hypotenuse we don't even have to calculate. We can recognize that it's going to be double 5. Now, if we are to label the angle theta, we can put theta in this corner of the triangle so that we can see the y component of E1 is adjacent to theta, and the x component of E1 is opposite to theta. Using the principle of vertical angles, we can see that this angle here is also theta. And from that point, we will be able to very simply determine both the cosine of theta as well as the sine of theta. The cosine of theta is going to be equal to the adjacent side, 8, divided by the hypotenuse, 10, and the sine of theta is going to be the opposite side, 6, divided by the hypotenuse, which is also 10. We'll determine the magnitude of E1 in the usual way as being equal to K times the amount of charge, 4 microcoulombs, divided by the distance of 10 meters, quantity squared. E1y is going to be equal to the magnitude of E1 times the cosine of theta. Plugging in the numbers, 9 10 to the 9 for K, 4 10 to the minus 6 for the charge, and 8 tenths for the cosine, we find that E1y is equal to 288 newtons per coulomb. This means that our final result, twice E1y, is 576 newtons per coulomb, and we're done.